Hi, in this video we're going to go over the 5-minute practice number 4, looking at the application of Huckel's rules to all these structures here. Okay, so I hope you've had a chance to take a look at this. Let's do the first one. This one may obviously look like benzene to you because it has the same structure, right? Like 3 double bonds and whatnot, but let's take a look. So whenever you have a heteroatom, the question is going to be that what is that hybridization of the heteroatom, right? Like that's going to be always the question. Is this sp3 or sp2? And this one is actually fairly easy to answer because that oxygen has a double bond. That oxygen has to have a p orbital to have a pi bond, right? Remember, double bond is made of a sigma bond and a pi bond. Pi bond is made of a side-to-side loose overlap of 2 p orbitals, 2 of the p orbitals, right, on 2 atoms. So for that reason, that has to be, this oxygen has to be sp2 hybridized. That means that there is indeed a p orbital on each of these 6 atoms that are conjugated. So it passes the first Huckel's rule or test that it's a conjugated, all the way conjugated ring. Everything has at least 1 p orbital on it. And the last criteria for the Huckel's rule, as you recall, was the number of pi electrons. If the number is 4n plus 2, n being any whole number, it could be 0 or 1, 2, 3. So if the number of pi electrons are like 2, 6, 10, 14, and so forth, then it's a pi. I mean it's an aromatic structure, and this structure has 6 pi electrons. So for that reason, this should be aromatic. What about the second one? Again, we want to ask the question, is this boron sp2 or sp3? Remember, sp2 hybridization is formed when you have 3 electron groups. This boron is attached to 2 carbons and a hydrogen, so it has 3 bonds, and if you draw out the loose structure of this, you find that there's no lone pair on that boron. So this has to be sp2 hybridized as well, and because there's no lone pair or anything, we're concluding that there is an empty p orbital. And remember, any atom comes with 3 of p orbitals, 3 p orbitals, right? So if you use 2 of them to make sp2 orbitals, sp2 hybridized orbitals, there's 1 p orbital that's left over. Okay, and then so this molecule then meets the first 2 criteria. Well, I guess assuming that it's planar, each of these 7 atoms, including boron, has a p orbital, or it's they're all conjugated, and there's really no reason not to be planar if this molecule can be aromatic. So let's count the number of pi electrons, right? There's 2 here for the bonds, 4, 6. And there's nothing on boron, so for that reason, there's 6 pi electrons total. And so this should be aromatic. Okay, this next one, this is not a heteroatom per se, but this has a lone pair and a negative charge. This could either be sp2 or sp3, and it would take an sp2 hybridization to put the lone pair electrons in a p orbital if there is a reason to do so, if it could be aromatic, right? But let's think about whether this could be aromatic or not. And to answer that question, we want to take a look at this carbon, because that happens to be absolutely sp3 hybridization, because that carbon has two hydrogens on it. In other words, there's no p orbital on that carbon, right? So this is not conjugated. Which makes this non-aromatic. Right, it doesn't even pass the first two tests of Huckel's rules. Sometimes people have the wrong impression that non-aromatic is worse than anti-aromatic or something, but the worst thing that could happen to you as a ring structure is you being anti-aromatic. That is an unusual instability. Remember, I'll refer back to chapter 17 notes. And being aromatic confers unusual stability. Non-aromatic, it just means you're not in either of those two categories. It's kind of like the biblical word Gentiles. If you're not a Jew, you are said to be a Gentile, like I'm a Gentile. But you don't have to be Japanese to be a Gentile. Just about anything can be anybody can be Gentile, as long as well, if you're not if you don't happen to be a Jewish person. So same thing. Non-aromatic just refers to just about any compound, if it's not aromatic or anti-aromatic. Okay. Now this next one, this one is a little bit tricky. Perhaps because we know that these two carbons absolutely have to be sp2 hybridized. So there's no question about that because of the double bond. But we do need to know what the hybridizations are for these two atoms, whether it's sp2 or sp3, and they have a choice because of the lone pairs what orbital they might put that in. If there's a benefit to becoming sp2 hybridized, they would. If there's a benefit to being sp3, they would. And that idea might be a little bit weird to you, but remember the reason why atoms sort of quote unquote decide to become hybridized is because there's an energy benefit, right? Stability benefits. It's all about what would benefit them as stability wise. Okay, so let's think about the possibility that either of these can be sp3. If either of oxygen or nitrogen, either of those two is sp3, then that breaks the conjugation, so this becomes non-aromatic, which is not like a bad or good choice. That's just not being aromatic, I mean, compounds like methane or water, those are non-aromatic too, but they're just as stable as just about anything else. So non-aromatic, it doesn't mean the worst thing, but if it could be aromatic, it would prefer that. So let's think about the possibility in which both of these are sp2, so that all four atoms are conjugated. Okay, then what happens? Well, then this one lone pair has to be in a p orbital, and then this lone pair on the nitrogen also has to be in a p orbital, whereas this lone pair on the oxygen must be in an sp2 orbital, right? Because there's total of 3 sp2 orbitals, so there would be 1, 2, 3 sp3 orbitals. 2 of those make up the bonds with carbon and the nitrogen, and one of them holds the one lone pair of electrons. All of that to say, we do have these 2 lone pairs in p orbitals, which means that this 4-membered ring is all conjugated, and there's 6 pi electrons. So therefore, this will be, even though maybe it doesn't look like it, aromatic. All right. What about this next structure? This is a bit weird, because it's a 3-membered ring, and that has a nitrogen with a lone pair on it. Okay. Now, is this sp2 or sp3 hybridized? And it's this time it actually is a good thing that it has a choice, because if it is sp2 hybridized and therefore it holds these lone pair electrons in a p orbital, then the total would have to be 4 pi electrons if we say this is sp2 hybridized. Okay, and that would make this, of course, anti-aromatic, which, remember, is an unusual instability. We don't want that. So what the nitrogen would do is to take on sp3 hybridization. Then this could just be non-aromatic. Okay, what about this next one? This has a carbon that is sp2 hybridized. This does have a hydrogen on it. Okay, with an empty p orbital, hence the positive charge, which means there's 2 pi electrons in this ring, and this is indeed conjugated, right? This carbon has a p orbital, this has a p orbital, and three-membered ring cannot help but being, there's no way that this is not planar, because you can't, 3 dots will always occupy the same plane, right? So for that reason, this is also aromatic, because 2 pi electrons, because 4n plus 2, if the n is 0, it can be 2, and then again 6, 10, and so forth, right? So that's aromatic. Now, at this point, some of you might be thinking, well, is there ever a possibility that you can have anti-aromatic compound? And there is, like, for instance, if there would be, like, if you had a structure like this, that boron has to be sp2 hybridized, and it has an empty p orbital, and this would have 4 pi electrons. There's nothing on boron, and so that would make this anti-aromatic, because it's pretty difficult for a 5-membered ring to not be planar. So all the 5 atoms here would have to be conjugated. So this would be an extremely unstable molecule. All right, let's think about this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-membered ring. Okay, so it seems like every single atom, or carbon I should say, is sp2 hybridized, which means it's all conjugated. So likely it's going to be planar, but let's think about the hydrogen that would have to be here. And these are pretty tight. And so it's possible, it's very likely that this is not going to be planar. Now, there would even be more incentive not to be planar if the number of pi electrons happen to be one of those anti-aromatic situations. So let's think about that first before deciding that this is definitely not going to be planar. So there is, let's see, 1, 2, 3, 4, 5, 6 pi bonds, which means what? There's 12 pi electrons. So, that is not 4n plus 2. It's not 2, 6, 10, 14, and so forth. It is, in fact, multiples of 4, right? It's a 4n pi electrons. So therefore, based on that, this should be anti-aromatic. And coupled to that is the fact that there's a really tight spacing of these 3 hydrogens. So all of that together, this likely will not be planar, so that these 3 hydrogens won't have to collide with each other or try to occupy the same space in the same plane. So therefore, we predict that this molecule, if it existed, it would be non-aromatic. Because the only other choice, if it forces itself to be planar, would be to be anti-aromatic, and that's worse than non-aromatic. But what about this one? Well, before we think about anything else, let's think about the hydrogen placement. And they seem to be kind of tight, but it's definitely better than the earlier situation. So then let's count the number of pi electrons. There's 1, 2, 3, 5, 6, 7 pi bonds, which means there's 14 pi electrons, which would make it aromatic. So even though this is sterically tight, it would try to be planar to enjoy the aromaticity. And this one, if you make a model, you'll notice that even though the two hydrogens are pretty tight, you can kind of make it planar. So it's likely going to be aromatic, but unless you actually synthesize this in real life, it's really hard to tell that this is going to be aromatic. In real life, when you synthesize this molecule, it's kind of somewhere in between aromatic and non-aromatic. So we'll just leave that question mark. And so some of you might be scared, thinking, well, are you going to ask us questions like that on the test? And no, the things that I would ask you about in an exam would be a little bit more obvious than these. So anyway, I just wanted to give you some like subtle have you experienced the subtlety of applying these rules?